Hello and welcome to Engineering Economy. This is Dr. Alec Hammerdiner. We will talk today about additional interest formulas. Recall that last time we learned about single payment compound interest formulas that helped us to understand how to move from one point in time to another point of time and be able to translate the present sum of money into the future sum of money and the other way around. Well, today we'll learn some additional useful formulas, including uniform series compound interest formulas, arithmetic gradient, and geometric gradient formulas. We will also talk about nominal and effective interest rates. We will discuss continuous compounding, and finally, we will talk on how to use spreadsheets for economic analysis. The learning objectives for today are as follows. We will solve problems using uniform series compound interest formulas. We also will be able to apply arithmetic and geometric gradients in modeling economic analysis problems. And we will also be able to understand nominal and effective interest rates and use them, and also will be able to apply continuous compounding. Last but not least, we will use spreadsheet to model and solve economic analysis problems. So let's take a look at this interesting story. Anne Schreiber was an IRS auditor, and she left more than $20 million to Yeshiva University after she died in 1995 at the age of 101 years, which is a pretty amazing age. So what she did is she started investing in 1944 in the stock market, putting $5,000 into the stock market. And here's the interesting graphic that shows of how the stock market, US stock market, was growing from 1900 to the 2000. So you can see, right, if it was somewhere in this area, right, at the beginning, then it started appreciating rather quickly and came to this level. So you can see the really amazing growth that the stock market, US stock market, experienced from somewhere from late 30s to the 2000s. And even though we have a stochastic trend, or stochastic, not really a trend, but stochastic history of the stock indices, it's still you can see that it's overall long term it has this amazing trend, towards rapid increase. And so to make the long story short, what kind of questions can we pose here? Was that using calculator or computer, can you estimate what annual rate of return would be to grow $5,000 into $20 million in 51 years? Is it closer to 20% or is it closer to 100%? Can you calculate what annual rate of return would be to grow $5,000 into 20 million in 51 years? And also, how does this average rate of return compare with the overall performance of the stock market during 1944 to 1995? Of course, these are very interesting questions, and they highlight the importance of being able to understand the time value of money and how the interest rate can grow your money. So here's a notation that we will use to learn a uniform series compound interest formula. A will denote an end of a period cash flow in a uniform series continuing for n periods. So every single period we would have this A, every single period for n periods. In the previous example, let's say we were investing something every year for 50 years, every year we would pay A, or deposit this A amount in into a an account, right? So every year it would be A, and the next year would be A, and then year after that we would always have this A invested at the end of the year. So if we drew a cash flow diagram, it would look kind of like this. We have n periods, right, because it's a general, and again, it could be years or it could be some other compounding periods. But let's suppose it's years. So we would have this n periods and also have a time now, which is denoted by 0. So then this would look like we have A at the end of year 1, A at the end of year 2, and so on, all the time, every year, throughout, including year n-1 and n. So every year we would have A, right? So that is why it's called uniform series, is because every time we have uniform, right, amount, A, it never increases or decreases, it's just A. Therefore uniform, and a series because it goes every time period we have it. So examples of these type of cash flows would be automobile loans, mortgage payments, insurance premiums, rents, or other periodic payments. Also, estimated future costs and benefits can also be represented as uniform series. So this is very important to understand, where you can see something like this. Now let's take a look at the formula specifically of how we can move from maybe present sum of money to these uniform series, and the other way around, or the future sum of money to the uniform series. So the first formula is uniform series compound amount factor, and it connects the uniform series A to the future sum of money F. So the future sum of money is what we're going to have at the end of n periods, and every time at the end of each period we're depositing A. So then in the future period, at the end of n years, we have the amount F. And this is a factor, here in the square bracket, this is a factor that connects them two. And so here, right, it's also written, but in a shortened form. So F given A at interest I over n years. Again, F given A at interest I over n years. So we'll use these factors soon, so you'll see how apply them. And another formula is uniform series sinking fund factor, and it actually is the reverse. Here we want to determine A given F. So we're finding A when we know the value of F, and this is basically, right, just an inverse, right, of this one, right? So this is inverse of this one. It's just like we took this and put it in a denominator. 1 over this is going to be this. And so again, this is A given F at I over n. So now let's take a look at an example that will help us understand how to apply uniform series compound interest formulas. 500 were deposited in the credit union, pays 5% compounded annually at the end of each year for 5 years. How much do you have after the 5th deposit? So let's draw a cash flow diagram. Yes, we'll have 6 different time points, starting with time point 0, then 1 at the end of year 1, 2 for the end of year 2, and so on, up to 5 years, and 5 will be the end of the 5th deposit. So what we're going to have is we have 500 deposited at the end of each year. So this 500 is going to appear every time, right? We're depositing at 1, 2, 3, 4, and 5. This is our uniform series. What we want to find is, right, how much we have after the 5th deposit. So we want to find equivalent future sum of money. Yeah, this is what we want to find. So now using the formulas, right, the future sum of money is the uniform series amount multiplied by the factor of f given a at I over n. Plug in I, which is 5%. Here annually, each period is a year, so this is exactly what we use, 5% here. And then we have 5 years, so 5 for the n, and that's what we have. And then finding this factor in your book on the page that gives you the 5% for values, right, for the discount factors, and looking at f given a, you'll get this value here. So then you just multiply to get this amount. All right, so following, we have another example of uniform series compound interest formulas. Jim wants to save money at the end of each month to pay for some equipment of $1,000 at the end of the year. If bank pays 6% interest compounded monthly, how much Jim has to deposit every month? Well, it says here, right, that we need to find how much Jim deposits every month. So we want to find a uniform series amount. Do we know F? Yes. See here it says that Jim wants to save money at the end of each month to pay for some equipment. $1,000 will be paid at the end of the year. So $1,000 will come at the very end there, at the end of the year. We're talking about compounding periods. So my question to you, well, I guess I already told you how many by showing this line, but the question here, right, is how many periods? Well, we're talking about compounded monthly, so we have 12 compounding periods over the length of the year. So 12 periods, and we include a 0 as a present time point. So now, right, we can draw 1,000 here as a future sum of money, and we can draw the ones that we're going to deposit, which are negative cash flows, right? The 1,000 we're going to withdraw at the end, so we're getting the 1,000. Here we're depositing them, so they're pointing down. And so we want to find the A. We're going to use this uniform series compound interest formula. So first, we want to find interest for a month. It says here 6% interest. Well, if it doesn't say here quarterly interest, then we assume that it's yearly. We always assume it's yearly if it doesn't say anything different. If it said here quarterly, you would think that 6% refers to the quarter, or if it says 6% monthly interest, we would think 6% for the month. But here it just says 6% interest, which means it's a compounded interest, and the compounding is in months. But the 6% is a yearly interest. So 6% is divided by 12 because there's 12 months in a year, and that gives us a monthly interest rate of 0.5%. So that's what we're going to use, and then the n is of course 12. So we got the I and the n. We can plug them in into sinking fund formula. So here A, we want to find the uniform series amount A given the value F. So notice, and that's going to be true for all the rest of the formulas. It's always going to be repeating in the same order. First you have A, then you have F here, right? So you have A equals F, because we know the F, and then it's multiplied by the factor. Again, you have A first, then F second. So every time it's going to be the same order. This is how easy it is to remember what discount factor to use here. You just write what you don't know, you say equals what you know, and then in the same order, you just rewrite A given F. And you don't even need to think hard about what discount factor to use here. So, and that's going to be true for all the rest of the different formulas that we learn. So just wanted to tell you that so that you keep that in mind. So again, A given F at I over N. So what is our F? Well, our F is 1,000. So we plug in the 1,000 here. We plug in 0.5 monthly interest that we just found. And we plug in, instead of N, 12, because we have 12 months. So now finding this factor in the book where it says 0.5%, there's a page that gives you the 0.5% discount factors, and then you look in the column that says A given F, and the row that says 12. And that's where you find this value. So you're using this here, multiplying it by the 1,000, you get $81.10. Alright, so next thing is to talk more about uniform series formulas that are a little different. And the reason why is because instead of using the future sum, we're now going to be using the present sum. So uniform series capital recovery factor, and that's why it's called capital recovery, because we're investing some capital at the beginning in a present. So here it will connect present sum of money with the uniform series amounts. So we can find the uniform series amount if we know this capital that was invested, right? The present sum of money. And again, this is the formula that you can plug in the values directly, or you can use the discount factor here in the brackets. And the discount factor is again found in the tables in the book at the end of the book. So again, A here, then P, and so here A and then P. So very easy to remember, you don't even need to think twice. If you wrote A equals P, then you continue in the same order, A given P. And then add I over N. And we have one more formula here that connects them in the other direction. If we know A, we can find P, and that's called uniform series present force factor. So now let's take a look at how we can use these new formulas. A machine costs $5,000 and has a life of 5 years. If interest rate is 8%, how much must be saved every year to recover the investment? So what's the question? How much must be saved every year? This every year is a clue to you that we're gonna have uniform series because it says every year. And then here it says machine costs this much. So we're gonna invest in this machine, right? This is gonna be our capital investment, right? And then we're gonna recover the capital every year by using the machine. So now we have 5,000, of course, would be pointing down at time 0, and then pointing, right, so pointing up, right, we have the savings over the 5 years. So again, 0, 1, 2, 5, right, these are our time points on the timeline, and now we can draw the 5,000, that's the cost of a machine, and we have to purchase a machine today. And then we're going to be using it, and every time we're using it, we're going to be saving something, right? So this is going to be pointing up, errors for AAA, equivalent, not equivalent, but uniform, right? So they're all the same size, uniform. So this is our uniform series. And therefore, we can use this. Plugging in the formula, we can find A from P, right? Given this I equals 8% and N equals 5. So that's exactly what we have. We find A given P. So again, here A equals P in the same order, A given P. And then at I over N. I is 8, N is 5. We plug in it in, finding in the book, plugging it in, getting the value. Alright, let's take a look at the next example. Should you spend $6,800 to buy a contract that pays $140 at the end of each month for 5 years if the desired return is 1% per month? So again, look, here the return is 1% per month. That's a monthly interest rate. So we're going to be paying a monthly interest rate. Right, this has this each month for 5 years. So there are 12 months in each year. So 5 multiplied by 12, we're going to have 60 as our N, right? And so let's take a look at this example again, right? It pays 140 at the end of each month. So that's our series amount, 140. So we need to understand whether this 140 each month for 5 years at the interest of 1 per month, is it equivalent to 6,800? To do that, we need to find the present value given this A, right? So you'll find the present value, and then we compare the present value to the 6,800 to understand whether it actually makes sense for us. This is our cash flow diagram. Remember, every time we always do the cash flow diagrams first so we can understand the problem better. It helps us visualize the problem, and it helps us also look at the problem and understand what's going on so that we know, right, what formulas to use. So we can see that the structure of the time series here, right, is we have every month, months after months, months after months, we have the same amount, which is a uniform series. And the uniform series amount is 140. We want to find how much it is as a present sum of money, so we compare it to this. We can't just multiply things or add things together throughout the 60 months because of the time value of money, right? They're not comparable like that. We cannot add them when they happen at different points of time. But if we put them in a specific point of time, then we can compare it. And the point of time we can compare it to is at present time, because the 68 that we would need, 6,800 that we need to have, we need to do it now, right, to buy this contract. So again, N is 60 because we have 12 months per year for 5 years, so 12 times 5. And then I is 1% because it says here per month specifically. The interest is per month. Before it didn't say per month, it said annually. So again, right, if we wanted to do that, right, we draw the cash flow diagram, and then we find P from A, because we know the A, and then P given A in the same order. If here we have P equals A, here we have P given A, it's the same order, PA, PA. At IN, plugging in 1%, plugging in 60, finding the discount factor in the book. At the page it says 1%. At the columns it says P given A. At the rows it says 60. We find this, right? Then we multiply these together to get this much. Now, it's very important that we compare this. This is just a little under 6,300, right? So 63 compared to 68. We're only gonna get a little under $6,300. So it's does not make any sense for us to spend 68. We would be losing over $500 if in fact we do that, right? So we're not gonna get this interest of 1%. If we had to spend less, then it would be better. But because we actually would spend more than what it's worth, it's not worth doing it at 1% per month. All right, very good. I hope you got this. So next example, right? If we have 6,800 that is paid for a contract that pays 140 at the end of each month for 5 years, what is the monthly rate of return? Right? If we do go ahead and pay 6,800, what kind of monthly rate of return would that give us? Again, a very similar cash flow diagram with this series, but now we have this P. We just don't know the I. We can set up the equation that connects the two and find the I from that equation. So we're setting it up, right? So here is actually equivalent. So we have this equal sign, right? So 6,800 is now equal to the future sum of money of 140 in terms of uniform series for 60 months, right? Or 5 years in terms of months. So we need to find I from here. Well, we can find discount factor simply by dividing both sides by 140. So that's obtained by dividing both sides by 140. So now we can look up in the book and see what we can find. Looking up in the book discount factors, we find that at I equals 0.5%, we get 51.726. And then at 0.75%, we get 48.174. So you can see that it's actually between these two. So it's got to be a little lower than 0.75%. And if we wanted to find it, we can use linear interpolation. And of course, it's just going to approximate, and we're not going to be able to find the specific I, but we can approximate, and it will lead us to a rate of return of 0.72%. And to do that using linear interpolation, it's pretty simple actually. So here I set up the equation of how to do it using linear interpolation for this specific example. So notice right here we want to find I. And we know that for I the discount factor is going to be 48.571. So the way to do it, right, is I minus, say, this other I here is the same as the discount factor for I minus the discount factor for the percent, 0.5 here. So that's how we're setting it up. And then we also plug in the other one, right? So for the I, instead of I, we then plug in the 75. So here we have 0.75, and here we have the P given A that corresponds to 0.75. So then it's very easy to set it up yourself for any other problem. So again, it's just the ratio of the differences is going to stay the same. And so we have here the i's on the top, the differences of p's, corresponding p's on the bottom, and the same here, the i's on the top, the interest rates on the top, and then the difference of the corresponding p given a's at the bottom. And it's not just for p given a. For any other factor, you could use linear interpolation in a very similar fashion. Alright, so let's talk about this next example. In this next example, a student is borrowing $100 per year for 3 years. The loan will be repaid 2 years later at a 15% interest rate. So here we have the years, and here we have corresponding cash flows. So we're borrowing 100 at the end of year 1, 2, and 3, and then we're gonna skip a year, and then we have to pay this what we borrowed, right? Pay including using interest rate of 15% annually. So now again we have 5 years, so we have 6 time points because we include time now, which is 0. So we have these 100, 100, 100. Then we want to know this future sum of money. So of course, in a way we would like for it to be similar to the uniform series, because it looks like uniform series. However, we can't take this uniform series and move them here in the future. Instead, rather than that, we can take all of these uniform series and move them here, right, at time 0. And that's exactly what we can do. And here's a solution. So in this solution, we're representing this as we could combine the time series together into the year 1. So by using these as a uniform series and just adding them to the A. Or we could just split them all separately, right? And we can translate A to F, this A to F, and another one a similar way. So in this way, if you split it up like that, we could use single interest formulas to move A to the year 5 from 1, to move A from the year 2 to 5, or to move A at the year move A at the year 3 to 5. So if we looked at this from this perspective, we would have this A looked at as a single rather than a uniform series as a single payment, and then use the formulas for the single payment. So it would be 100 f given p, because we look at this as a p rather than a uniform series now that we split it and only look at a single one at a time. And then 15%, and this one, if 1 is now 0, then this is going to be 4. So this becomes 4 because we can move and we can have this 1 as a new 0, then the 2 will be the new 1, then the 3 will be the new 2, the 4 will be the new 3, and the 5 will be the new 4. So therefore we have 4 here. So that is the amount, that is the future amount for this single amount, the future amount of sum for this a at 1. Similarly, this is amount for the single amount, this is the future amount for the single amount at 2. And because between 5 and 2 we have 3 years, this is going to be n3. Here between 3 and 5 we have 2 years, so we're going to have 2. And so again, because we have these, all of the discount factors that we see here in this formula, they're all found on the same page, on the page that lists the discount factors for I equals 15%, but they're different because they're all in different rows, right? They're in the same column f given p, but they're in different rows. This is in row 4, this one in row 3, and where do they disappear? And this one in row 2. And then we evaluate all together and get this amount. So notice 459 and 20 of 20 cents. So now there's a different solution. As I noticed earlier, right? We could represent this as a series amount where we could move it all together to the future amount at time 3, or at the present amount at time 0. So if we move it all together, take it all together, we move it to the future amount at time 3, and then later move it to 5. That's what we're gonna get. F3 is gonna be 100, and then this is again, now it's A because we're combining it, we're moving it to 3, so it's gonna be find the future amount from the uniform series at 15% over 3 years, right? Because this is 3 years and that's at the end of year 3. So now we'll get this, and this leads us to this. However, it's not at year 5. We want it at year 5. We have it at year 3. So we still need to move from F3 to year 5. But compared to 5, F3 is just in the past, or more as a present sum of money. So that's exactly what we would have in that case. Then we would move F3 to 5. And so again, this would be the present because it's before the future, and this would be the future amount. So then we can find f from F3 that we just found. So F3 is now the past, right, or the present amount. So this, we look at it as the P. This F3 is actually representing the P. So we have f given P, f given P, right? 15% and 2 because there's 2 years between 3 and 5. And so the 3 would be the new 0, the 4 would be the new 1, and the 5 would be the new 2. So now, right, if you look up the discount factor f given p, that's on 15% page in the row 2, that's what we will find. And then plugging it in together, we'll get $459.20, exactly the same as the solution 1. And here is another example, example for 7. What amount P needs to be deposited in a saving account that pays 15% interest to support 3 later withdrawals? So here's the cash flows, right? So cash flows minus P, then 0, then 20, 30, and 20. These are the cash flow or withdrawals that we want to have. So if we have it like this, this is a cash flow diagram. We can have, again, different ways that we can find the equivalent amount, right, for the present sum of money that would be equivalent to these withdrawals. at 15% interest rate, of course. Here's solution 1. We could, for example, represent it as 3 separate single payments. 3 separate single payments, just like before for solution 1. And then move them all to times 0. This one to times 0 and this one to times 0. They all would be looked at as future amounts, right? So then we would need the single payment formulas, and in fact that's what we're using: P1, P2, P3. This is P1, this is P2, this is P3. We basically are just moving this 20 at 2. We're going to represent it as a present sum of money P1, and so on for the rest of them. So 20 multiplied by this discount factor, because 20 is a future. We have P given F, right? P given F. F is 20. P equals to F. Or in this case, this is actually P1 and this P. So if you look at this as P1 is in the present, this is in the future. So the future sum of money, we need to find the present. Present, F. So we have 15% too, because, right, this is N for this one, N is going to be 3. For this one, N is going to be 4. And so those are the main differences. And of course, here we have 30 rather than 20. So then, finding the discount factors from the book and estimating it, we'll get $46.28. So now, solution 2. We could actually look at it from a different point of view. We can look at it first, move them all to the future, and then move the future to the present. So first, moving 20 to F1, moving 30, and then this is already F3. So again, similar way, in this case we don't need to multiply by any discount factor because this 20 is already at the required time, and then we can add them all together because they're all are going to be at time 4. So it doesn't really matter. Before we were adding them all at time 0. Here we're going to be adding them all at time 4, so we can do that. And this is why we have the pluses. So again, plugging in the values and then looking up the discount factors from the table, we get this value, which is exactly the same as in the solution 2. Here's another thing that we need. Well, it's not quite the same because we still need to move to the P. So I apologize for that. It's not quite the same, right? So, but as soon as we move our F that we just got to the P, we'll get the same. So now, right, this is the F, this is a P. Using single factor formula, we get P from the F. Again, PF, this is very, very straightforward. 15%, we're moving it from 4, so this is 4. So this is our F from before that we got, multiplied by the discount factors that we looked up in the table. And this is 46.28, which is exactly the same as before, right? So 46.28, if you look at the solution 1, oh, sorry. This is what we got after doing it using solution 1. And that's exactly the same as what we got using solution 2, right? So there's different ways that we can do the same problems. So many ways to actually solve a problem often exist. So to demonstrate that, let's also come up with another solution, solution 3. So in this case, we can represent it as moving it first to P1, right? So we can move it all to P1. We can split it up into this, and then move it, right? Why are we moving it to P1 like that? Because, right, we can move, we can move the series only immediately to the preceding year, right, to the beginning of this year 2, which is the end of year 1. So that is why we're moving it to 1. So now we take the series formula here, and this is just a single payment formula. And that's exactly what we have, right? You look, this is going to be in the square brackets is what we're going to have as a P1. Square brackets gives us P1. And then P1 we're going to translate into P by multiplying it by P given F, because P1 then becomes the future, right? Compared to the P1 is a future sum of money. So we connect P1 right? If we know P1, we can get P. P1 is a future sum of money, so it's P given F, because P1 is actually looked at as F. And we only move it 1 year, so it's going to be P given F at 15/1. And so that's what we have. It carries us over. So everything in the square brackets right here is actually our P1. And the way we got it is by looking at it this way, right? The P1, when we look at this from the P1 perspective, this becomes a uniform series. And this is just a single payment. So uniform series amount is 20. This is 20. This is A. We're going to find a P, right, from it, for it. So P given A, 15% over 3 years, 1, 2, 3 years. And then here, this is a single payment over 2 years. So this is 2 here. And then just plugging in the discount factors that we found in the book and multiplying and adding everything together. And again, leads us to $46.28, just like we would expect. All right, let's talk about the relationship between compound interest factors. So in terms of a single payment, we have this relationship for the single payment. And that's simply, right, they're inverses of each other. And you noticed it before when we discussed it in a previous chapter. In terms of uniform series, the relationship is also simple in terms of looking at A given P or P given A. It's also the inverse relationship. And the same for F given A versus A given F. That's inverse relationship. But then it becomes a little more complicated if you look at uniform series and represent them as through single payment discount factors. And this is actually a little complicated, but don't get alarmed. This big sigma is actually just to denote the summation. This is a Greek letter that denotes the summation where this t changes from 1 to 2 to 3 to 4 and so on, up to whatever n we have here. So if n is 5, then we would have t where all those discount factors where t would be 1, 2, 3, 4, and 5. If n is just 2, then we would have p given f I at I over 2 and p given f at I over 1. If this is 3, we would have p given f at I over 1 plus p given f at I over 2 plus p given f at I over 3. And similar way, we can actually represent the discount factor of f given a as 1 plus the sum of the f given p's, right? So f given p's are single payment discount factors. And also notice that we can move from a given p to a given f by just adding an I. So now let's talk about arithmetic gradient. Arithmetic gradient is a different type of structure. If before we talked about uniform series, meaning that we always had this same payment, with the arithmetic gradient we actually have this linear trend. And it could be increasing linear trend or it could be decreasing linear trend. If we have increasing linear trend, then this g amount is going to be positive. If it's a negative, if it's a decreasing trend, the g is going to be negative. So this is arithmetic gradient. Arithmetic gradient can be split into the uniform series and then the gradient amount. So notice the uniform series always start at 1, right? Here we have 0, uniform series start at 1, go all the way to 5. But the gradient amounts start at year 2 and keep increasing linearly from g to 2g, 3g, 4g, and so on. Basically, this is going to be n minus 1g, right? N minus 1, if n is 5, then n minus 1 is 4. All right. And examples of arithmetic gradient series is operating and maintenance costs. Sometimes they are linearly increase in time, or salary packages might have this linear increases. So notation, we have g. It is a fixed amount of increment or decrement per time period. As I said, it could be positive or negative. If it's positive, it's increment. If negative decrement. And so here again we have a timeline, and the G starts at 2. There is no G at 1. At 1 we just have 0. And G always starts at 2, and then we have 2G at 3, and so on. At n-1 we have n-2G, and at n we have G multiplied by n-1. So let's take a look at the formulas. Arithmetic gradient present force factor formula connects the P and the G. So G is a gradient series. So of course, right, this is only the gradient amount that we finding. We still need to add the uniform series, right, if we do have the uniform series there. And so you can see this is a very long formula here for the discount factor, but you can look it up, and there's in the book there's actually discount factors, so you can just use the discount factors from the book. And this is P given G at I over N. And here's another formula, and this formula actually connects the A and G, and that's why it's called arithmetic gradient uniform series factor, right? Here's the present force for the present sum of money. This says uniform series for the uniform series amount. And so again, very complicated, very involved formula. You don't have to remember it. Instead, you can look it up in the tables. Here's the discount factor from the tables. A given G. Again, A here, G next. So the same here, the same order, A, G. So if we have A equals G, then here we have the same order, A given G. And of course the same here for the present force factor. So here's an example of the application of these factors. So we have the following cash flows. If we draw the cash flow diagram, which of course we would start first with drawing a cash flow diagram, this is what we have. If you notice, you can see this linear trend. If you subtract 120 from everything, right, you subtract 120 from every cash flow, here you get 30, then you have 60, then you have 90, and then you have 120. So you can see this a linear increase for the 30s that we have. It grows each time linearly. And that's exactly what we have. 30, 60, 90, 20, right? After we splitting this, so we split these cash flows into a uniform series and the gradient amounts. This gradient is 30. This G is 30. At time 3, it's going to be 2G, which is 60. At time 4, it's going to be 3G, which is 90. At time 5, it's going to be 4G, which is 120. All right. So now we can find the present amount. We need to find the present amount of uniform series. And so this is a present amount of uniform series. This is a uniform series amount. And then this is the A. So P given A, right? We're finding the equivalent present force of this uniform series. So P given A, 5% over 5 years. And this is a geometric gradient amount. So we again finding the present force of that. So this is a G. So P given G, 5%, 5. Plugging in the discount factors that we found from the book, we got this. And then multiplying and adding, we get this value. So that's how easy it is to use arithmetic gradient interest factors. So here's another interesting example. Notice what happens here. Wow, you're right. What we have is we have decrement, right? So rather than increment in terms of gradient, we have a negative gradient because this 24,000 is actually going to be what we have at the very beginning of the year. So it's going to be our A. And if in fact this is what we're going to have, we represent this as uniform series with a uniform series amount of 24K, and we have the negative gradients. So it's going to be pointing down starting at year 2. So between 24,000 and 18,000 there's 6,000 difference. So minus 6,000, then minus 12, minus 18. So you see it's decreasing. This is our negative 6,000, that's our G. Then multiply by 2 is going to be 12, negative 12. And then multiply by 3 is going to be negative 18. Exactly what we expect. So this is our G, gradient amounts. So we need to find the, actually, in this example, we want to find the A. So we can convert the G into A. This is already as A, and then we're converting it into A. Again, why do we want to do that? Is maybe sometimes it's more suitable to try to understand in terms of the uniform series, right? And represented as yearly, the same yearly expenses or the same yearly benefits that we get every year, even though we might have some kind of structure that has some trend. So now this negative 6,000 is a G. We want to find equivalent in terms of uniform series that would be equivalent to this gradient. So we're finding the uniform series that is equivalent to this gradient. And that's why we're multiplying by A given G. The 10% is what we just given in this problem is the interest rate, and then this is 4 years. So even though it starts at 2, it's still n is over 4, because this is how we expect the uniforms, the gradient amount is to start at year n, and then we transferring them into these negative, equal negative. So this would be equivalent. What we are finding here is we finding equivalent of these, where we're splitting them in the same exact amount over 4 years. And so plugging in the value for discount factor and then multiplying, subtracting it from 24,000, we get this much. And that's exactly the uniform series, right? That if we had the uniform series that had at year 1, 2, 3, 4, we had 15,714 every year, they would be exactly equivalent to this arithmetic gradient. We would have no difference, or no, at 10% interest rate, we would have no preference of whether we have payments like this or whether we have uniform series of this amount at 10%. But at different percent, it might be, we might have a different view on those two, but at 10% they're equivalent. So here's another example where we're using arithmetic gradients interest factors. So these are cash flows. Now notice that they start in year 4 and end in year 7. So this is how they look. We want to find the present amount. So what we can do is notice, right, that we could split them up again if we had a year and now, right, at 3. Right, we could look at this as a arithmetic gradient if our now would be at 3. Right, so if a new 0 would be a 3, and then in that case the 7 would be the new 4, right, the 6 would be 5, the not 5, sorry, 3, the 5 would be 2, and the 4 would be 1. So that's exactly what we get, right? We're just representing it like this. So we have 150 at years 4, 5, 6, and 7, and then we have the gradients 25, 50, 75. So we can move it to P3, right? We cannot move it right away to 0 because it doesn't look like the structure that we would assume. If we were able to move it to 0, we would also need the gradient as a uniform series starting at 1 and then the gradient starting at 2. That doesn't happen. But if we look at it as a uniform series that could be moved to 3, then that would work, right? So that's exactly what we're going to do. We're going to first find P3. So we find P3, this is our A uniform series amount. So finding the present sum of it, given the A. So we have P given A, 10%, 4 years. And then we have 25, again, P given G, because that's G, gradient amount, 10%, 4 years. And then summing it up, we get the P3. So that's the value right here. So now we converted all of these, and these. We converted them to this single payment P3. P3 compared to P is a future sum of money, right? And so we can get a P from P3, looking at P3 as a future sum of money. So this is P, this is P3, so P given F, because P3 is future compared to P0. And of course we need to move 3 years here, so over 3 years, so here we have over 3, and plugging in discount value of the discount factors that we found in the book, we get this. Alright, one more thing that we wanted to talk about is geometric gradient. And geometric gradient, in a way, is somewhat similar to the previous things that we looked at, for example, arithmetic gradient. However, rather than linear growth, we now have exponential growth. So G is going to be a constant growth rate, which could be positive or negative for a period. A1 is a cash flow at period 1. So now we have A1 multiplied by 1 plus G, A1 multiplied by 1 plus G to the second degree, and so on. At n minus 1, the 1 plus G is going to be taken to the degree n minus 2, and at n, the 1 plus G is going to be taken to the n minus 1's degree. So you can see, in fact, we have this exponential growth, or we have this growth rate of G. So geometric gradient present worth factor is a complicated formula. Notice that for a geometric gradient, there is no discount factors in the book, and that is because in addition to I, we also have G, right? So depending on G, there will be too many tables for us to have at the end of the book. We need just like a separate book just for that. So now, just for the geometric gradient. So there is no, don't look for the tables of geometric gradients, there is none in the book. So here it's important whether I equals to G. If I does not equal to G, if they are two different values, then this is the formula we would use. But if I equals to G, then this is what we're gonna have, right? In fact, if we try to use this formula when I equals to G, we would get a 0. Right? We would not want to do that. We would not want to have 0 in a denominator of a fraction because we cannot divide by 0. So of course we cannot use this formula when I and G is the same value. But when I equals to G, we just use this very, very simple formula here. Alright, so let's use it. Using 8% interest rate, calculate the present worth of maintenance cost of the first 5 years, where the first year's cost is estimated at 100 and increases at a constant rate of 10% per year. Well, very simple. 8 is interest rate, right? The growth is 10% per year, so the G is 10%. So I does not equal to G. So using that first formula that we had, right? This first formula is what we have, because I doesn't equal to G. And in fact, we're using this formula. And what is our A1? A1 is the first year's cost. And that's estimated to be $100. So that's exactly what we're plugging in. We're plugging in 100. We're plugging in G equals 10 because it says this first year's cost increases at a constant rate of 10% per year. So G is 10%. So we're using G, 10%, 10%. And then I is interest rate. It's 8%. 8 right here, and right here also 8. And plugging this all in, computing these values, we're gonna get $480.42. Alright, that was an example of geometric gradient. Now let's talk about an important two concepts that are often being confused by students. And specifically I'm talking about nominal interest rate versus effective interest rate. So far, what we've been using a lot is this effective interest rate. And that's I. It's denoted by I. But the nominal interest rate is denoted by R. The nominal rate is actually a rate per year without considering any effect of compounding. And I is the effective interest rate per compounding period. So far, we've been mostly using effective interest rate. I sub A denotes effective annual interest rate, taking into account the effect of compounding. and M is the number of compounding periods per year. So how do nominal and effective rates are connected? We can find the I from the nominal rate when we divide it by the number of compounding periods. So our nominal rate divided by number of compounding periods M will give us effective interest rate per compounding period. We can also find effective annual interest rate taking into account the effect of compounding. We're using the following formulas. It just right this 1 plus the fraction of r over m, and the sum is taken to the nth degree, and then from this exponent we're subtracting 1. Alternatively, we could look at this, right? This r over m just represents the I, which is effective interest rate. So we can just put the effective interest rate here per compounding period, right? If compounding period is months, we're using the monthly rate here to find effective yearly rate. And then we have number of compounding periods. If if compounding is monthly, if this is I is a effective monthly rate, then M must be the number of months per year would be 12. Again, we're going to take a look at this in more detail and look at some examples. But for continuous compounding, we're going to have a very different effective annual rate. For continuous compounding, there is no compounding periods. There's infinitely many of them. And therefore, the formula is E, which is the exponent, right, the natural exponent, approximately 2.72 hundredths. So it's e to the r, which is the nominal rate, minus 1. Well, let's take a look at this table. This table actually gives us the nominal rate and the effective rate. So the nominal rate of 1%, 3%, and so on, and here the last row is 25%. So the yearly rate, right, is the same as the nominal rate. But if we look at the compounding, if we compound twice per year, semi-annually, you can see that the effective rate is larger, right? Larger than 1%. This 26 and some is larger than 25%. When we compound 4 times per year, it grows even larger in terms of effective rate. When we compound daily, this is the rate. When we compound continuously, it's even larger. But notice, right, when we start compounding daily compared to continuously, it's pretty close. It's not that close, but it's pretty close in terms of the rates between daily and continuously. And so, again, let's take a look at the example so we can understand how to use these nominal and effective interest rates. Because as I said, these are the concepts that many students find very difficult. So if I give you $50, you owe me $60 on the following Monday. So how do we find the effective rate? Well, weekly interest rate, right, we can find it as follows. It's just 60 minus 50, right, the difference that we get in 1 week divided by 50, and that's 20%. That gives us a nominal annual rate of 20% multiplied by 52 weeks. 10,040%. 1,040% just a nominal annual rate. We can find effective annual rate by plugging in the values that we have, right? So if we have weekly, this weekly interest rate is how the compounding happens, right? Is every week. So that's an effective rate, effective weekly rate. We plug in it here. There's 52 weeks, so M is going to be 52. The 20% is our effective weekly rate, and from there we can find effective annual rate. So estimating this, it's going to be a whopping 310,400%. And so that's quite a huge percent And now, if you look at the end of the year balance, if you were to continue investing this way or borrowing this way, we would owe from the $50. If we capped at $50 for a year based on this agreement, we would owe at the end of the year a whopping $655,200. Pretty impressive, right? So again, how did we find it? Just single interest payment formulas. F given P, right? This is a discount factor that we all know well. And so using the weekly rate, right? This is effective rate that we would be using, and the N is the number of weeks. So here you go. Now let's talk about continuous compounding interest formulas. We have several formulas that are kind of similar to the formulas that we found, except that we're not going to have the 1 plus I there, but instead we're going to have a lot of exponents. So exactly the same, right? Except instead of I, we're going to now use R and nominal rate. So F given P, we can find F, future sum of money, from the present sum of money, multiplying it by this discount factor, which is continuous compounding discount factor, F given P, Rn. Right? When you see R, must be continuous compounding, and this factor is E to the Rn. So next is a single payment present worst factor. So somewhat similar, except here we have minus, the degree is minus Rn. We also could look at continuous compounding sinking fund, and that connects us with the uniform series amount. So uniform series given the future sum of money, and that's the discount factor for that. And a continuous compounding capital recovery, and that's the present sum of money. So finding the uniform series amount given the present and the nominal rate over n years. And also continuous compounding series compound amount, and that's when we want to find F given A. And continuous compounding series present worst when we want to find P given A. Right, so again, a lot of exponents. Here's an example of how to use continuous compounding, right, based on these formulas that we just saw. How much would be in the account for $2,000 deposit in a bank that pays 5% nominal interest compounding continuously? So again, how much would be in the account for 2,000 deposit? So if we have 2,000 deposit, right, at 5% nominal rate, the R is 5, the P is 2,000. So the future amount of money depends on N, right? If it's 2 years, for example, like in this example, it's 2 years. We can have P plugging in 2,000 instead of P, plugging in 0.05 for 5% instead of R, and then 2, and that gives us $2,210.40. Or alternatively, we could use it in a different way, right? We could turn it from the continuous compounding into this effective annual rate using this formula, and then use the effective annual rate. All right, and effective annual rate actually assumes that we compounding per year. But we once again would get the same exact value using this approach. So as I said, there's often many ways to approach the same problem. Here's another example of using continuous compounding. How long will it take for the money to double at 10% nominal interest compounding continuously? Well, to double means that we will need to set up an equation. If we have some sum of money, let's say P at present, at the future we want to have 2P. That means it would double. In fact, right, we have F equals P, right, using this formula, and we would get 2 because we would cancel off if we plug in instead of F 2P, we're going to cancel off the P's, we're going to get 2. So it would be E to the 0.10 because it's 10%, and then n. And so we set up this equation. So on one side we have e, on the other we have 2. To get rid of the exponent, we need to take a natural logarithm from both sides. So taking logarithm on both sides, for this side we're gonna get this product here that we have in a degree. Here we have a logarithm of 2, which evaluates to this. So then we divide this by 0.10, which gives us 6.93 years. Or, of course, there's always a different, well, not always, but very often, there's a different alternative way to do the same. We could convert this from continuous compounding into yearly by finding effective yearly rate. And that's the connection between for continuous compounding. It would be e to the r minus 1. And so plugging in r of 0.10 or 0.1, we would get this. And then we can plug this I into the formula. So here's another example. We have $500 that were deposited in a credit union that pays 5% compounded continuously at the end of each year for 5 years. How much do you have after the 5th deposit? So here again, what we need to find, right, is the future amount, because it says how much you have after the 5th deposit, and we do it for 5 years. So we depositing 500 at the end of each year, so it would be A. It would be O. Oh, let's go back, okay, to this problem. So it would be A, right? 500 would be A. And then we're finding f given a with a nominal rate r because it's continuous compounding, and n is 5 years. So plugging all this in into the corresponding formula for f given a that we just looked at a couple of slides before. Right, so here again, a is 500, and plugging in the values for r and n, which here you have 5%, so 0.05, and then n is 5 years. So 5 here, and plugging it in, evaluating it to this. Or alternatively, again, we could find, convert it to the I effective interest rate using this formula for continuous compounding. We get this interest rate of 5 points and some additional values, right? And we're plugging it in into this formula between the f and a, right? Again, this is f and a, instead we just have, instead of r, we just have an I there, but it's the same exact formula, just the I here. So not quite the same, because, you know, we have different ways to compute it compared to the continuous compounding, because this is not continuous anymore, because we are not using a continuous rate, we can using an effective annual rate here. But once again, it all relates to the same value, because these are just two different alternative solutions. Whichever solution you like better, that's the solution you should use. So now, last but not least, I wanted to briefly talk about spreadsheets for economic analysis. Turns out that Excel has many ways to do economic analysis. First of all, you can construct tables of cash flows, and then you can use annuity functions to calculate P, F, A, N, or I. And you can use block functions to find the present worth or internal rate of return for a table of cash flows. Also, you can make graphs for analysis and presentations. So there's a lot of very useful things that you can do with spreadsheets. And last but not least, you can calculate what ifs for different scenarios. So here are some of the Excel functions that could be used to do the engineering economic type of problems. Here PV stands for present value, so this allows us to find present sum of money based on A or F, right? F is an option, and again, if you want to find F, then you gotta skip the A, and by skipping I means you still have comma, then you have space, there's nothing for A, then comma, then you have to use the F. And then the I and N is, as always, I is the effective interest rate, N is the number of compounding periods. PMT stands for payment, and that's the uniform series amount that we can find. So we can find A, again given I, N, and either P or F. If right after N you have comma and then the value, then it's going to be finding the payment based on the present sum. But if you have two commas after N, then it will assume that you are given the F here, and it will find the uniform series amount from the F. So if you want to find it from the future amount, then you have to have two commas, comma, comma, and then the F. And you can find the future amount again from IN, either A or P. If you're finding it from P, then it's going to be two commas, because here you're just skipping the A. Or if it's going to be A, then you just have IN and A. You can also find number of periods, which gives you the N, given I, A, P, or F. And then you can find the rate, interest rate, from N, A, and P, or F. And optionally, you could have a guess there. A guess and basically where it would start, where the algorithm would start to compute the rate. So this is what I wanted to tell you today. And note that the type is actually the number of 0 or 1. And it's important to remember that the stop indicates when payments are due. If you use 0 or not use anything at all and just have it by default, the type is set to 0, which means end of the period. But if you have a beginning of the period, then you would need to use 1. And then also, Microsoft Excel can solve for one financial argument in terms of the others, which means, for example, using something like this, where we have the P multiplied by the discount factor of F given P, and then A multiplied by the discount factor of F given A plus F. And that's very important to remember, because of that, you want the negative signs to be added to find the equivalent values in P, A, and F. So keep in mind, right, that you would need to add the negative signs here for A, for P, and F. So if your payments here is $100, instead of 100, you would say minus 100. All right, so that's pretty much what I wanted to talk about, except two additional functions that we also have, and these are known as block functions. And the block functions is because they're using a range of values. Like there before, we only had a single value, but the block functions allows you to use a whole range. So you have some kind of range, and you can find a net present worth for the range of values. Or you can find an interest rate based on the range of values, and again, an optional guess. And guess is where the computational algorithm is going to initialize. You can put a certain guess as your interest. So these are the block functions, and I encourage you to use Excel, especially in terms of the game that we might have, or that we plan to have in this course. I think these would be very helpful to you. All right, thank you very much, and I'll hope to see you soon.